Okay, so this is the Python data structure and algorithm class. And today we're going to talk about sorting. All right. Before we get started, so let's see. So what is sorting, right? Typically, you're giving a, randomize the data and you want to sort them in order. And presumably those data can be compared. One is less than the other or greater than or equal to, and then you can put them in a sorted order. So that's called sorting, right? For example, you have a list of numbers. That's a typical example, right? Sorting. If you want to sort these numbers, what are you gonna do? Okay, let's do it manually first, and then translate into code. So, any ideas? How will a human do it, right? Anyone want to volunteer? Like, what's your algorithm to sort it? Samoa, do you want to volunteer? Tell us how are you going to sort it by hand, given this list of numbers?
Well, first of all, I'll take the smallest, which is -3, and then take the second smallest, and then third smallest, until we get to the last part.
That's good. Hold on a second. Strategy is every time go through the list, pick the smallest item in the list, right? So let's do the manually. So what's the smallest here? It's -3, right? Okay. Then after you take the -3, you want to pick another smallest, which is 4, right? And after -3 and 4 is picked, in the rest of the thing, you pick the smallest, which is 6, right? And so on and so forth until you get 99, which is the biggest, and you sort them out. What's the time complexity of your algorithm? You have to go through this many times, assume, right? Because every time you pick how you pick the smallest in the list, it's easier said than to ask a computer to do it.
So it's big O n, and n is the length of the list. So
it's O of n to pick the smallest, isn't it?
Yes. So there's also monkey sort out of random probably, and there's also bubble sort and a lot more sort.
So it's O of n. Every time you pick a smallest, it's O of n, right? Worst case. I'm talking about worst case. Okay. So if you're given a list that's in a reverse sorted order, and every time you go to a smallest, you have to go all the way to the end of the list and pick one, right? And that's the on and -1, -2. But overall, we'll say it's on every time, and you do it n times, right? Because every time you only pick one, and there's n numbers, so you would do it n times. So that's order of n square. Do you understand this? You have to do it multiple paths, and you do it n times. So n times. So basically, you have a nested for loop, right? For I, let's define a function called Zemo sort, right? Zemo sort algorithm. Zemo sort with L is the list, right? List, okay, of integer, for example. And let's say from typing import what list, right? Invalid syntax. Anyway, that should be working. List of integer, right? And then you're not returning anything because you're doing you get to change the sort. So as Zmo says, we want to pick a smallest number, right? Let me get the length of the list, okay? That's the list. So I can do I in range n. Does it make sense? So I give a for loop. I'm looping through all the numbers in the list. That's outer loop. Okay. Every time I want to pick a smallest, so I'm gonna say smallest. Instead of the number, I'm gonna do an index because it's index. Initially, I say I is my smallest index. Okay, I is like every time I pick the first one, right? I pick the first one. I don't know yet. I suppose this is the first one, is the smallest. But then what will change the condition? Okay, so now in this inner loop, you all know what the multiple loop, right? In the loop, we're gonna pick the smallest one, right? Okay, so I'm gonna iterate through the list. Again, the list in range what? Okay, let's think about it. So for another loop, I'm gonna pick the smallest one, right? And if L of j, which is the current number, is less than L of smallest index, okay? So if I find an element that is smaller than I randomly picked one, then what do we do? Okay? And then after the for loop, right? If something, and we're gonna do swap. Okay, something. All right, and then I think that's it. I'm gonna finally return a L, right? So that means I'm gonna return a list of integer that is sorted. Okay. So do you understand this code? Basically, what this is a implementation of Zmo says, right? I'm gonna pick the smallest number every time in that range. Now, what should be in that range? Say I'm at the index 0, right? Okay, I'm in the index 0. I say the small index is 0. Okay, the first round, and j. So now I'm going to compare this to the rest of the list, right? So for j, I'm going to say, so if the index is I here, then this will be I plus 1, right? So I'm going to search from I plus 1, the one after him, all the way to what? All the way, all the way to n, right? Now remember this range n is not included because the last element is n minus 1. From 0 to n minus 1, that's n elements, remember? So range I plus 1 to n is basically the rest of the numbers. For the rest of the numbers, I'm comparing one by one to this smallest index, which is the first one I pick. If any of them are bigger than it, I don't do anything because the smallest one is didn't change, right? I'm still the smallest one. However, as soon as you find an element in this rest of the list that is smaller than this, then I'm gonna what? I'm gonna say the smallest index now changes. This one is not the I anymore, is j. Does it make sense? So after this for loop, I'm guaranteed to have the smallest elements. Now, if the smallest element is not equal to I, so initially it's I, right? If it's not equal to I, then I'm gonna change. I'm gonna swap what? I'm gonna swap the number at that index with the smallest index, right? Because I want to actually swap them. So in swap in Python is very, very simple. So it's L smallest index, L I, right, is equal to, I swap with I. because I picked I as small index, but now it's not. So every time it's not, then I'm gonna swap it with I. So just do A, B equal to BA. So basically this is like A part B equal to BA. So you swap the number from A, B to BA. So A become B, B become A. You can, this is unique in Python. In other languages, you have to use a temp variable like temp equal to A equal to B, and then B equal to temp, right? So you need this kind of 3 steps to exchange A and B, but in Python, you can do it in one go. So it's beauty of Python languages. Does it make sense? Swap the number. Okay, so after that, you can return L. And then that finished the sorting. Let's test it with some sample. Let's define a main function, right? Basically, you test it. And then in the main function, you want to have L equal to, let's give this array a go. Copy paste. Okay, and then I'm gonna print Zimo sort, and then with L. Okay. Actually, I'm gonna give them a copy, so I'm gonna give a reference. I want to give a copy, and then of course, if name equal to main, I'm gonna call main function. All right, let's test it out. I have to run it specifically into DSA, and I'm gonna do Python 3 sorting.py, and you can see -3, 4, 6, 17, 17, 26, 28, 19, 9, which is sorted. Let me see, print f before sorted, and then I'm gonna give them the L. Okay, and then after sorted, and then give them a return value of that. Okay. See if I can do it better. Yes, before sorted is this, and after sorted is this. Any questions, Zimo and everybody else?
Can we maybe measure the time for Zimo sort?
I'm sorry, can I say it again? Can we what?
Can we maybe measure the time? Using time.
Very good idea. Very good idea. Okay, let's measure the time. How do we? Let's put a time here. Tick 1 equal to time dot. What's that? I have to import something, right? From datetime, import datetime. Is that right? Let's Google it. Python time module. Import time get time. Okay, let's see what time is better. Let's use the epoch time. Epoch is the point where the time starts as platform dependent. Windows Unix system epoch January 1st, 1970. So from this time and on, it's a counting, right? Leap second not counted. So let's do a time GM time 0. Or just say time dot time. Okay, simple enough. Import time. Import time and time dot time, right? So that's just tick 1. And then sorry, tick 2 equal to time dot time. And then print used tick 2 how many time it's a tick 2 minus tick 1, right? Okay, dot format, right? Okay, let's run it. 2.55 times 2 to the power of minus 5 is really, really small. Okay, we need a big data. We need a very big data to sort it. Very good. How to generate? Oh, you know what? I have ideas. Let's generate a random. Let's define a function to generate a very big numbers. Okay, very good. Let's say get big data. Okay, so let me define this function. Get big data. Okay, so how to define how to generate big data, right? So how to generate a big list? Well, L is equal to let's say a list X for X in range. Let's say how many data I want to generate, like those big numbers, right? So I have that list, and L dot shuffle. Let's import a random function. Random. Let's see how to use a random function. Python random number. Generate random number, right? Let's see, random number. Random rand range. Random rand range 110. Okay. Let's see Python random shuffle. Random dot shuffle list. Okay, good. I'm gonna just do L random dot shuffle of my L and return L. Okay. So we can generate a number, and I'm gonna print. We're not gonna print all the numbers because it's too big. We just print first 100 numbers. Well, just first maybe first 10. Okay, let's run it. Oh, it's gonna take a long time. Wait, it may outside the CPU. Let's just give them a small number. 9,000, right? Oh, wow, look at that. Why there is so many numbers? Shuffle L. Did I print? I print L all the way to 10. Why?
I think it's because you said print before sorted L.
Ah, okay, yeah, that's why.
You might want to get rid of that. after it's sorted. You just want to do it, how much time it takes. You don't want to print that whole thing.
Right, and also print time also takes time. So let's just do a sort. So I'm only interested in sorting, right? So I'm gonna do a sort and then print the time. So I don't want to count the time to, yeah, okay. That makes sense. So I'm not gonna print, I'm not gonna print after sorted, because that's too big. I'm just only sorted and then print the time, okay? I'm only printed the first couple of times. So let's run it. No, I'm not gonna run this. I'm gonna run this. Okay, the first 10 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, first 10 is like that. And it's gonna do sorting. Let's say how many ticks it's taking to finish the sorting. It's taking a long time, right? It's really long.
I think it's because the list is really long.
I'm sorry, because what?
I think it's because the list is really long. And
yeah, of course. It's
and
9,000.
But even if most of the numbers, yeah, it's looping through. So I think maybe we should add some breaks. If needed.
Maybe it's the second. This is the second, maybe. So it takes like 45 seconds to finish. Does it feel like 45 seconds? Or maybe it's 1 minute, right? Anyway, let's say 999, 1,000 data, okay? 1,000 data. 1,000 should be okay. 1,000 is only take like 0.29 seconds, less than 1 second. If we give it a 9999 and run again, it takes much longer. It's like 10 times longer. But that would be, but why, right? I give them 10 times bigger numbers, but I don't know.
Maybe because it doesn't only count about n, it also counts how random n is. And since
you know what? Because we already analyzed that this worst case scenario is n squared. Although my n is 10 times, but the square is like 100 times more, right? So this is about right. It's 100 times more. So it's about 29 seconds or 30 seconds. Does it make sense? See, this is actually works because although n is 10 times more, right? But the time is running time is n squared, right? So it's the time is 100 times more. Now you can see it measures 31 seconds instead of 0.3 seconds. Make sense? So it's actually in line with our sorting algorithms. Okay, let's go back to 999 or 1,000 data. Okay, let's run again. This time it should be taking like 0.27 seconds. Okay. Let's do maybe twice, 2,000. Then it will take 4 times longer, right? So 4 times 0.3, 1.2. It's about right, isn't it? 4 times longer. So if we get them 5 times longer, it's 25 times longer. 25 times longer is gonna be, I don't know. Maybe 10 seconds. Yeah, 8 seconds. Okay, so let's sorting 5,000 number in our Zemo sort. Actually, there's a name for it. This is called selection sort. Do you understand why it's called the selection sort? Sorry, Zemo, you're not the first one to implement this, to thought about this. So somebody before you already write a paper about this. So it's called selection sort. Okay.
It's literally the exact way we all sort.
But that's not the only way, right? Let me define a bubble sort. It's actually not better. It's like, why it's called a bubble sort? Define bubble sort. So let me introduce bubble sort, which is taking L. Again, it's the list of int. By the way, the list can be a linked list, right? I can tell you some other things, but right now it's just a regular list. Okay, so let's talk about bubble sort. What is bubble sort? Well, the idea of bubble sort is still order of n squared. So basically, instead of pick the smallest number, every time I would think about a stone sink to the bottom or the bubble goes to the top. Every time I go through the list and I'm picking the biggest number to the right and leave the smallest number behind. Okay, so basically I go through this list once, right? -3 is less than 99, so I don't swap. 99 is bigger than 6, I swap 6 and 99. And then if 99 is bigger than all of them, then at the end of the day, I will move 99 all the way to the end. So I swap every single one when I'm comparing to the next. And once it's done, this is done, and I'm gonna go to the rest of the list and do the same method again. So every time I have the heaviest one to the right, and if right is the bottom of the lake, you can think about you sink the heaviest stone to the bottom every time. Or maybe the lightest one will be on the left. So it's the same thing, right? So it's a bubble all the way to the left. So it's called a bubble sort. All right. So let's implement this again. N is the length of L. And for I in range of N, right, you have to do a true for loop. And I'm gonna say a Boolean called swap is false. So we're not swap yet, right? For J in range of let's say 0 to so basically J in the loop, right? Every time you make the one element at the end is fixed, then you can forget about this one. So as the I is moving on, you are actually in minus I minus 1. Okay, J in range that. So compare. Compile, whatever. Compare. Right? So if compare what? Lj, if Lj is greater than Lj plus 1, so I'm comparing my current number with my next number, right? So J plus 1 is always less than I, less than, yeah. J plus 1 is less than n minus I, okay? So if Li is greater than that, that means I'm heavier than you. I'm gonna sink to the bottom. I'm saying swap equal to true. I did swap and I will swap. So Lj and Lj plus 1. I'm gonna swap the neighbors, okay? You can see this disadvantage is there's a lot of swap happening here. Right? Again, you should be familiar with this swap scheme. And then, so why I have this? So if any point, if there's no swap happening, what does that mean? If you go to the whole list, there's no swap. That means what? That means every single one number is in place. It's in the order, right? Because if you have any pair that's out of order, you will be able to swap. You will need to swap. So if there's the fact that there's no swapping, it's already sorted. So if it's already sorted, you can break the loop early. You don't need to go next. It's already sorted, right? Else, if it's not, if there is a swap, that means you still have things to sort it. So you're not done yet. pass, right? I don't want to do anything here. And then at the end, I'm going to return L, right? I don't need this anymore. So this is bubble sort. Any questions? Let's compare it with selection sort. Let's do it with bubble sort. This should be comfortable. Bubble sort. And then this is selection sort. So the idea is the same. They are about the same complexity, but yeah, let's run it. Let's see which one is faster. Come on. One is 8 seconds, I know. So selection sort used 8.188 seconds. Bubble sort used 17. Wow. It's even worse. It's like double the time. Why is
I didn't expect that. I mean, I hope bubble sort was gonna be like,
yeah, bubble sort is no better. It's actually is worse. Okay, let's just forbidden bubble sort. Let me introduce a better algorithm. Let's do, I guess, merge sort. Merge sort. Okay. L is a list of int. I'm gonna return a list of int. And all right. So what is merge sort? Well, merge sort has 2 steps. One is called, of course, merge. Well, that's the second step, right? And one is called one is just the call itself, right? So the idea is that we divide and conquer. What does it mean? If you have a list, the idea is I want to split list into half. Okay, think about this. Similar to our binary search, right? We're gonna do a cut half. So let me use that as a example. Right? Again, use this list as example. So what I mean is, okay, I have this, right? But then I'm gonna cut it in half. So the left half containing this for data, the right half containing this for data. Okay, so far so good. Now I'm gonna divide this again into this for subgroup. Are we done yet? No, I'm gonna continue divide into a list of 1 element. You see where I'm going? All right. So as you can see, in original list, I split it into half, and then further I split this into half, and further I split it into half until I only get 1 single element. Then I'm gonna do the reverse. I'm gonna merge these 2 together, so I become minus 33. Minus 3 and 99. Right? And then I'm gonna merge these 2 together, and this 2 and this 2. So I get this same thing again. So from top to bottom is split. Now I'm gonna do merge, right? I'm gonna do merge this, and then I'm gonna merge these two. When I merge these two, I want to make sure these are in order, right? So -3, 6, 17, 99. So the left one is, so you can see I'm only sorting it in the merging step, right? I don't do any sorting in the split stage. I only do it after I split them into all the way, right? 26, 27, 28, and 17. You see, these are sorted already. And then finally, when I merge the whole thing, I get -3. So let me manually merging them together, okay? So how do I merge as a human? When I look at the left and I look at the right, and I pick the first element from each list. Why? I'm guaranteed to know if the first element is smaller than the first element there, this is the smallest among all the elements, Zemo. I'm merging it, right? But I have to make sure that they're in order.
Well, then you could do it with 6 and 4. 6 and
so first of all, I compare the first element in the left list and the first element here, and -3 is smaller, so I pick -3. And then I compare the next element with the first element here, but 4 is smaller, so I get 4, right? So let's manually do it. And then next is 17 here, but next is 6 smaller, so I put 6. You see what I'm doing here? And then 6 and 17 are equal, so it doesn't matter which one you pick, right? And then 99 and 28, 28 is smaller, so I pick 28, finally 99, and I sorted the whole thing. I did a little bit fast, but do you see the idea here? Do you agree? That's how you merge them into a sorted list, right? So okay, so let's program this. The first step is to divide it into 2 lists. How do I divide into 2 lists? Well, I'm gonna using the recursion. Remember what recursion is, right? So I can do merge. I can so recursion involves 2 key points. One is you have to make sure you have a base case, okay? And then second is you can do a recursive call. So what is my base case here? So when do I stop recurse? Merge sort. This step, right? This step means I only have one single element list. Then I don't need to sort it anymore. It's already sorted, right? So I want to, again, get the length of this list. If the length is less or equal to 1, that means it can be empty list or list of single element. I'm gonna just return L because I was already sorted. Otherwise, I'm gonna do L1 is merge sort something. L2 is merge sort something. And then finally, once they are all merged, I'm gonna return merge. I'm gonna merge L1 and L2. Okay, and that's the whole merge sort, right? So the merge sort, what we're gonna put into parameter? We divide it in half. So the left half is L something and right half is L something. Can somebody help me finish this code? We start from 0 to all the way to the middle of the number, right? Middle number is n divided by 2. Okay, that's not included. So for the right half, we include this NDLI2 and all the way to the end. Does it make sense? So we split into half. We translate the code like this. And every time I call the merge sort, I will, if it's not a single element, right? I keep doing this division to the left and right. And then at the end, it is single element array. I can just return that. And then after that, I'm gonna merge L1, L2. So merge -3 and 99, I got this. And then merge this and that, I got that. And then merge this and that, I finally got this. So, and it returns. So that's the whole idea, okay? So how to do the merge part? Merge part is the most interesting thing when happen. You are sorting this when you're doing a merge. Well, we already did it manually, so we can translate that manual gesture into a code, right? This is the part that takes practice. All right, so want to merge list 1 and list 2. Two lists, right? List 1 and list 2. Okay, return a list. First of all, I'm gonna get the size of the list 1 and list 2, right? And L1, oops, L1, comma, sorry, length of L2. Okay, we know the size of these two lists. And then I use the two helper pointers starting at 0, 0. You see what I'm gonna use it. And then the answer will be put into a new list, okay? So I'm gonna keep doing I less than N and J less than M. So these two are iterating through this two list, right? Every time I going through, I have 2 pointers. One is starting from left to right to scan this sub list, and one is I gonna scan on this list. So if L1's I is less than L2's J, right? So if this L1's I is smaller, then I'm gonna append this L1I to that answer. And then don't forget, I'm gonna increment the pointer to the left list, right? If there's other way around, right? I'm gonna append the L2J and then J plus equal to 1. So either every time I either pick the leftmost element or the rightmost, the leftmost element of the left array, L1, and or the leftmost element in the L2. And the reason I can do that is because I know anything beyond that is still even bigger, so I don't need to worry about that. Okay, so after I did that, at the end of the while loop, then if I is still less than N, that means there's something left, right? Something left in the left element. Because they are already sorted, I can simply extend my list with the rest of them, right? Else if J is less than M, so if J is still not empty, I can extend this L2J to the end. Again, finally, I'm going to return the answer, right? This answer is a list which is already merged and sorted. Does it make sense? So the merge actually do most of the work on sorting. This recursion is just a split into, divided into a smaller piece so you can do it one at a time. So that's the whole thing we call the merge sort. All right, let's try run it. Merge sort. L. Okay. Let's try, I see merge sort. Yes. Let's see. Okay, so before we even do this timing, can you tell me, make a guess, is it faster or slower than selection sort? And why?
I think it's slow because you have to do a little more math. You gotta cut it in half again and again. And yes, you know, the worst case when it's all backwards. If it is there, it could take longer because I always bigger than all less than all of bigger than you gotta do a lot more switching here. So
Okay. So you think it's slower than the selection sort. You still think your initial sort method is the best, right?
Surprised it could sort 1,000 words and 1,000 numbers in just
All right.
8 seconds. I haven't made many interventions that fast.
Okay, let me ask you this then, Zimo. The way you divide it in half, how many times you need to divide a 8-element list into half?
Well, 8
until you get a single list.
8 divided by 2, so or a double divide 8 into 8.
Actually, it's already here, right? We divide, this is 8-element list. We divide this 3 times and we get this division done.
Yes, but to do, yeah, I did some recursion stuff and
so let's say this merge function, okay? Let's say this merge function. How many times you need to merge? It's also 3 times, right? You only need to merge 3 times to get this done. So all in all, you only need to do log of n to do the division and merge. And for the merge, because you have to go through every single number, so every time it's O of n, right? So you have to go through every single number. So overall, if you multiply together, why multiply? Because you have to merge every time. It's like 2 loops. So overall, it's O of what? N log n. Do you agree? This is a complexity for this merge sort instead of n squared. So the time saving part is to divide it into half actually and merge. So it's log n because 8, 2 to the power of n is n. 2 to the power of n equal to n. So if n is 1024, n equal to 10. Okay, so 2 to the power of 10 is 1024. You have to remember that number. Yeah, so don't you agree this analysis is n log n complexity? Does it make sense?
yes.
So which one is faster, n log n or n squared?
Now I think it's actually the merge sort because n log n is smaller than n to the power.
Very good, n log n.
Yes.
So you can expect it to go faster. Let's test it, okay? Okay, moment of truth. Can it beat 8 seconds? Oh, wait a second. Why I cannot share? Python 3 sorting .py. No such file. Oh, Python 3 sorting .py. Let's see. Da da da. Look at that. Select and sort in 5 seconds. It's actually doing its best. However, look at the merge sort, 0.09 seconds. Wow. It's order of magnitude faster, right? It's not 1 second. Let's do okay. Because it's so fast, I'm gonna do this later. Cut. Okay, I'm gonna do the second, then do the merge sort first. And then I'm gonna increase the number. Let's increase that number to double it, right? 10,000. All right, let's run it. Merge sort is already done, 0.06 seconds. Whoa, woo, woo. Why is this even faster? That doesn't make any sense. Oh, look at it.
Because some computers actually learn, so the computer's learning from it. So if you use a function enough, the computer will try remembering how the function works, and the computer will kind of go faster and faster. We learned that with selection sort, it going faster and faster. Yeah.
Well, in this case, it actually goes slower. Let's run again. We randomize the number. So see, this time it takes 0.17. So it's a little bit slower. But then look at this selection sort. It's so slow.
That bubble sort won't stand a chance.
Yeah, did not stand a chance. 20 seconds. Actually, it's much better. Well, it's worse. Okay. Actually, let's get them a fair game, right? So let's see how. Let's get 10,000 data. But this is actually let's get n, right? So I can select the n for this generation. So this is 1,000. This is L1. And L2 is generate big data. I give 10,000. This is 5,000. Let's say 3,000. This is 100,000. Let's do 5,000 and see which one is faster. So I give L1, give L2 to merge sort, give L1 to selection sort, right? So it's not a fair game, but let's see if they can even. Oh, L is not defined. Oh, okay, yeah. I don't even need to print this. Okay, not run, but clear. Come on. So it takes merge sort 1.5 seconds to go through 100,000 data, and it takes 3.41 seconds for selection sort to go over only 5,000 data. So as you can see, a correct algorithm that is inherently faster, like n log n, can be potentially much faster than n squared. So you see the difference. You see importance of selecting your algorithms, because you can always say, hey, my computer, I can get a faster computer. But yeah, using a faster computer, you can even compute it faster with a faster algorithm, isn't it? Hopefully you learned something today. And I think next time we'll talk about more sorting, like quick sort and sort with linked list. Okay, so can you talk about what you learned today? Like, what's your takeaway from this class? Like any questions are welcome before we adjourn.
Well, I'm just asking, how many faster ways are there than merge sort that you know of? Like maybe
there's more than one way, right? There's a quick sort that we're going to talk about next. You can Google search quick sort. It's the same magnitude though. It didn't make faster than merge sort. I think n log n is the fastest worst case scenario that you can do. But even it's the same magnitude, you can make you can tune your algorithm even better, right? You can maybe cut in half. So there's actually tons of sorting. Bubble sort, shuffle sort, and also what else? Sleep sort, right? So sleep sort is a very interesting one. So you can ask every number to sleep that number of seconds. So if it's 1, they only sleep 1 second. If it's 10, sleep 10 seconds. And you print it out by the time they wake up. Then you're sorted, right? So number 1 only wait 1 second to wake up. And the bigger number, the So that's called sleep sort. So yeah, you're welcome to look at, and there's also order of n sort, provided that you don't need to do comparison. Actually, there is a proof that you can think about any sorting method based on the comparison, right? Because on either one, we compare what? We compare the number. We have a swap and comparison. If you based on the swap comparison, the best you can do is n log n. That's the best we can do. The virtually is the best, or some other n log n. But if you're not doing the comparison to do the sorting, then you probably can do not constant, but on. On is the best. So if you want, we can talk deeper into like counting sort and other sort. So yeah, Google search all these sorting, and maybe your homework is introduce a sorting method that you have researched, okay, and demo it. All right, that's it for today, and 2 more minutes, but I'm gonna share this link so you can go play it, play with it. And then of course, don't forget to search other sorting method that it's out there, an interesting sorting method, and maybe implement 1 or 2 on your own. Okay, you're free to do that.